The calculations required to perform an ANOVA by hand are tedious and prone to human error, and even the graphing calculator can be cumbersome for all but the smallest data sets. For these reasons, it is common to use statistical software to calculate the F statistic and the p-value. So here's example 5. It says the table below shows an ANOVA summary to test whether the mean of on-base percentage varies by player positions in Major League Baseball. Using the table, what can you conclude about the different positions? Okay, so notice that the group is the positions and the error is what we call residuals. So the DF column is the degrees of freedom column. Okay, this whole thing is what we would call an ANOVA table. Okay. And you'll notice that the number 3 is here because I have 4 groups, 4 positions that I'm looking at, and 4 minus 1 equals 3. The mean square column, so this is what's known as the MS column, and the first row of that column would be the MSG column. The MSG column is equal to the sum of squares for the groups divided by the degrees of freedom for the groups. And then the MSE would be similar down here. So MSE would be the sum of squares divided by degrees of freedom. For the F value, this, remember, is calculated as the mean square for groups divided by the mean square for errors, and so that would equal 0.00252 divided by 0.00127. Okay, and then this final column here where it says PR and then in parentheses greater than F, that means the probability that we are greater than the test statistic. This is what's known as the p-value. So this is calculated using the FCDF command and then putting in the test statistic 1.984 and then a big number and then the degrees of freedom 3 and 323. So in general, the mean square column is equal to the sum of square divided by the degrees of freedom. The F is calculated using the mean square from the group divided by the mean square from the error. And we talked about the PR column, and that is the p-value column. And we calculate that using the FCDF command. There are 3 conditions we must check for an ANOVA analysis. The first one is that all observations must be independent. This is always important for all the tests that we've done. Number 2, the data in each group must be nearly normal. This is important when the sample sizes are small. But if the sample sizes are large, then this aspect or this condition is not that important. And number 3, the variance within each group must be approximately equal, especially important when sample sizes differ between groups. Here's example 6. Caffeine is the world's most widely used stimulant, with approximately 80% consumed in the form of coffee. Participants in a study investigating the relationship between coffee consumption and exercise were asked to report the number of hours they spent per week on moderate, in other words, for example, brisk walking, and vigorous, for example, strenuous sports and jogging, exercise. Based on these data, the researchers estimated the total hours of metabolic equivalent tasks, or MET, per week, a value that's always greater than 0. So the table below gives summary statistics of MET for women in this study based on the amount of coffee consumed. So we can see that there are 5 groups. So each column is a group besides the total column. So less than or equal to 1 cup a week, that's the first group. 2 to 6 cups per week, that's the second group. 1 cup a day, third group. 2 to 3 cups a day, fourth group. Greater than or equal to 4 cups a day, fifth group. So part A says write the hypotheses for evaluating if the average physical level varies among different levels of coffee consumption. So the null hypothesis would say that the mean of less than or equal to 1 cup per week is equal to the mean of 2 to 6 cups per week, is equal to the mean of 1 cup per day, is equal to the mean of 2 to 3 cups per day, is equal to the mean of greater than or equal to 4 cups per day. And then the alternative hypothesis is that at least one mean is different from the rest. Part B says check the conditions to proceed with the test. First, we have independence. Well, this study did not seem to be random. So there was no random selection or random assignment. So this is a big question mark. Does it satisfy nearly normal? Well, this is a large sample. So normality is not an issue. Equal variance? Well, the standard deviations are fairly equal. So if we look back at the table from before, we can see that the standard deviations are fairly equal. Remember, the variance is just the square of the standard deviation. So we can check that one off. Part C says below is part of the output associated with this test. Fill in the empty cells. Okay, so for degrees of freedom, remember this first row is the groups row. We know that there were 5 groups, so 5 minus 1, that equals 4. The residuals group is the sample size minus the number of groups, so n minus k. So that would be 50,739 minus the number of groups, which is 5. So that would be 50,734. And so if I add this column up, I get 50,738 degrees of freedom. The sum of squares, the first box is blank, but we do know the total. So if we take the total, 25,575,327, minus this second number, 25,564,819, we would get the first number, which is 10,508. For the mean square, what we would do is we would take the sum of squares for the groups divided by the degrees of freedom for the groups. That's going to be the first box. So if I take 10,508 divided by 4, then I get 2,627. And then in this other box, we would take the sum of squares for the errors divided by the degrees of freedom for the errors. So that would be the 25,564,819 divided by 50,734. And that gives me an answer of about 503.9. Okay, now the F value is calculated by taking the MSG divided by the MSE. So the MSG is the 2627 and the MSE is the 503.9. So when we divide those two, we get an answer of about 5.21. So if we put that and we use it in the FCDF command, that will allow us to calculate the p-value there. What is the conclusion of the test? So because the p-value is less than 0.05, we would reject the null hypothesis in favor of the alternative hypothesis. There is sufficient evidence to show that at least one mean is different. There is sufficient evidence to reject the idea that no matter how many cups of coffee women drink, their exercise habits are the same.